Good afternoon. Alright, so let's just get this microphone set up correctly. There we go. That should be better. Let's just dial that in a little. Alright. Welcome to episode 3 of Learning Rust. Last episode, we covered the common programming practices, or concepts, including data types, functions, comments, control flows, mutability, and variables. This episode, we are going to be covering Chapter 4 of the book. This is going to be understanding ownership, and we'll find out what that means in the Rust ecosystem shortly. Okay, so ownership is Rust's most unique feature. It enables Rust to make memory-safe guarantees without needing a garbage collector. Therefore, it's important to understand how ownership works in Rust. Okay, so without needing a garbage collector, we can do memory-safe guarantees. Let's check that out. So Rust's central feature is ownership. Although the feature is straightforward to explain, it has deep implications for the rest of the language. All programs have to manage the way they use the computer's memory while running. Okay. Some languages have garbage collection that constantly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free memory. Rust uses a third approach. Memory is managed through the system of ownership with a set of rules that the compiler checks at compiler time. None of the ownership features slow down your program while it's running. Fantastic. Because ownership is a new concept for many programmers, including myself, it does take some time to get used to. The good news is that the more experienced you become with Rust and the rules of the ownership system, the more you'll be able to naturally develop code that is safe and efficient. So it's very key semantic in Rust to understand ownership. Okay, so we're definitely going to take a lot of time to understand this. I can probably stream for about an hour and a half. So when you understand ownership, you'll have a solid foundation for understanding the features that make Rust unique. In this chapter, you'll learn ownership by working through some examples that focus on very common data structures, strings. Alright, so the stack and the heap. In many programming languages, you don't have to think about the stack and heap very often, but in systems programming languages like Rust, whether a value is on the stack or the heap has more of an effect on how the language behaves and why you have to make certain decisions. Parts of ownership will be described in relation to the stack and the heap later in this chapter. Okay, both the stack and the heap are parts of memory that are available to your code to use at runtime. But they are structured in different ways. The stack stores values in the order it gets them, thus the stack, and removes the values in opposite order. This is referred to as last in, first out. Think of the plate analogy. The more plates you add, you have to take it from the top. Adding or removing plates in the middle or the bottom wouldn't work as well. Adding data is called pushing to the stack. Removing is called popping. Okay. That all makes sense. All data stored on the stack must have known size and fixed size. Data with an unknown size at compile time or a size that might change must be stored on the heap instead. The heap is less organized. When you put data on the heap, you request a certain amount of space. The operating system finds an empty spot in the heap that is big enough, marks it as being in use, and returns a pointer, which is just a memory address of the location. This process is called allocating on the heap and is sometimes abbreviated as just allocating. Pushing values onto the stack is not considered allocation. Because the pointer is a known fixed size, you can store the pointer on the stack, but when you want the actual data, you must follow the pointer, and that's where we get dereferencing Think of being seated at a restaurant. When you enter, you state the number of people in your group, and the staff finds an empty table that fits everyone and leads you there. If someone in the group comes in late, they can ask where you've been seated to find you. Pushing to the stack is faster than allocating on the heap because the operating system never has to search for a place to store new data. The location is always at the top of the stack. Comparatively, allocating space on the heap requires more work. Because the operating system must first find a big enough space to hold the data and then perform bookkeeping to prepare for the next allocation. Accessing data on the heap is slower than accessing data on the stack because you have to follow a pointer to get there. Contemporary processors are faster if they jump around less in memory. Continuing the analog, consider a server at a restaurant taking orders from many tables. It's most efficient to get all the orders at one table before moving on to the next table. Taking an order from A, then an order from B, then A again, B. It's slower and inefficient. When your code calls a function, the value passed into the function, including potentially pointers to data on the heap, and the function's local variables get pushed onto the stack. When the function is over, those values get popped off the stack. Keeping track of what parts of code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. So it seems like ownership is strictly about the heap. Once you understand ownership, you won't need to think about the stack and the heap very often. Okay, so maybe it is stack as well. But knowing the managing heap data is why ownership exists, can help explain why it works the way it works. Okay. First, let's take a look at our ownership rules. Keep these rules in mind as we work through examples that illustrate them. Each value in Rust has a variable that's called its owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. Okay. We've walked through an example of a Rust program already in Chapter 2. Now that we're past basic syntax, we won't include all of the function main codes in the examples. So if you're following along, you'll have to put those examples inside the main function manually. As a first example of ownership, we'll look at the scope of some variables. A scope in the range within a program for which an item is valid. A scope is the range within a program for which an item is valid. Okay. Let's say we have a variable that looks like let s equal to hello as a string. The s variable refers to a string literal, where the value of the string is hard-coded into the text of our program. The variable is valid from the point at which it is declared until the end of the current scope. On 4-1, comments annotating where the variable s is valid. Yeah, okay. So, allocate onto the heap. I imagine, well, it's not mutable, so it's fixed size, so this might be stack. Do stuff with s, scope is now over, and s is no longer valid. In other words, there are two important points in time here. When s comes into scope, it is valid. It remains valid until it goes out of scope, and that's block scope. At this point, the relationship between scopes and when variables are valid is similar to that of other programming languages. Now we'll build on top of this understanding by introducing the string type. The string type to illustrate the rules of ownership, we need a data type that is more complex than the ones we covered in data type section. Then that was in episode 2, the previous episode. The types covered previously are all stored on the stack and popped off the stack when their scope is over. But we want to look at the data that is stored on the heap and explore how Rust knows when to clean up the data. Okay, we'll use string as an example. here and concatenate on parts of the string that relate to ownership. These aspects also apply to other complex data types provided by the standard library and that you create. We'll discuss string in more depth in Chapter 8. We've already seen string literals, where a string value is hard-coded into our program. String literals are convenient, but they aren't suitable for every situation in which we may want to use text. One reason is they're immutable. Another is that not every string value can be known when we write our code. What if we want to take user input and store it? For these situations, Rust has a second string type called string. This type is allocated on the heap, and as such, is able to store an amount of text that is unknown to us at compile time. You can create a string from string literal using the from function. Okay. So let's do this. So we're going to make a directory for ownership. And then we'll cd into there. And then we're going to, I guess, actually what I should do is I should remove ownership. And then I should cargo, is it cargo create? Cargo new. Cargo new ownership. So if we cd into ownership, and then we can vim source. Okay. So this is going to be this guy. So if we cd into ownership and we cd into source, can I just cargo run main? Okay, and then we'll print line s. Right. I'll get used to this one day. We have to put our token in the string and then print the line. Okay, so that works. And then if we were to cp, so we'll cd into source, copy main to main2 rs, and then cargo run main2. Yeah. Perfect. So we'll remove main2 .rs and just vim main. Okay, so we can see that this works as expected. Okay, so the double icon is an operator that allows us to use namespace, particular from function under the string type rather than using some sort of name like string underscore from. Okay, we'll discuss the syntax more in method syntax in Chapter 5. This kind of string can be mutated. Okay, so it is mutable. Okay, so let's mess with this. So we're going to touch a file called immutable strings.rs, immutable strings. Okay. So function main, and then let's see, e main, yep, and then let s equal testing, and then with that we can then print line our token s cargo run immutable strings, Now, if we try to say s is equal to something else, we get a failure. I kind of expected that to be a little bit more of a failure, but it's not. But if we say let s equal something else, oh, what am I doing? Why is it? It's running main rs. So let's research that. Rust run a single file. Some other file, not only main rs. Add this to your TOML path. Vim. Let's see, cargo, TOML. Then we'll just paste in this. Is it indented like that? No. And our directory is just source, immutable strings .rs, and then we will cargo run. Bin.name is required. We will do this another time. Name equals ownership. Okay, there we go. Consider prefixing with an underscore y, unused variable s, in immutable strings. This guy. Okay. S plus. Does it let me do that? No. We'll figure concatenation here in a little bit. But basically, if we do this action, we're going to get an error. Cannot assign twice to an immutable. And we'll leave it there. Okay, so now we can do strings push string, and we can do that on main. So we switch over to main.js, or main rs, and we say s.push string, I think it's str, sure is, and we say hello space world. We have to put that as a function, and we'll get rid of that space, and then we'll run. Now, yeah, that makes sense. So if we vim our TOML and we just say change to a period, and we want to say main.rs, now will it run? Cannot compile ownership. Cannot borrow as mutable. Do I have to say mute? Yes. S is mutable. Let S mute, or let mute S. Let mute S. And now we can run. Now we get hello world. Okay, so that makes sense. So what's the difference? Why can string be mutated but literals cannot? The difference is how these types deal with memory. In the case of a string literal, we know the contents at compile time, so the text is hard-coded directly into the final executable. This is why string literals are fast and efficient, but these properties only come from the string literal's immutability. Unfortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time and whose size might change while the program is running. With the string type, in order to support mutability, growing piece of text, we need to allocate the amount of memory on the heap, unknown at compile time, to hold the contents. This means the memory must be represented from the operating system, or requested from the operating system at runtime. We need a way of returning this memory to the operating system when we're done with our string. The first part is done by us. When we call string from, its implementation requests the memory it needs. This is pretty much universal in programming. Okay, yeah. From. So here, we're going to the operating system and getting memory. However, the second part is different. In languages with garbage collectors, the garbage collector keeps track and cleans up the memory that isn't being used anymore. And we don't need to think about it. Without a garbage collector, it's our responsibility to identify when memory is no longer being used and call code to explain or explicitly return it. Just as we did to request it. Doing this correctly has historically been difficult. If we forget, we'll waste memory. If we do it early, we'll have an invalid variable. If we do it twice, that's bug 2. We need to pair exactly one allocate with exactly one free. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our scope example from listing 4-1 using string instead of a string literal. Scope is now over, and S is no longer valid. There is a natural point at which we can return the memory our string needs to the operating system. When S goes out of scope, when a variable goes out of scope, Rust calls a special function for us. The function is called drop, and it's where the author of string can put the code to return the memory. Rust calls drop automatically at the closing curly brace. Okay. Note in C++ patterns of deallocating resources at the end of an item's lifetime is sometimes called resource acquisition is initialization. Resource acquisition is initialization. The drop function in Rust will be similar to you if you've used RAII patterns. This pattern has profound impact on the way Rust code is written. It may seem simple right now, but the behavior of the code can be unexpected in more complicated situations when we want to have multiple variables use the data we've allocated on the heap. Let's explore some of those situations. Ways variables and data interact move. Multiple variables can interact with the same data in different ways in Rust. Let's look at an example. X is 5, Y is X. We can guess what it's doing, bind the value of 5 to X, and then make a copy of the value in X and bind it to Y. We now have two variables, X and Y, both equal to 5. This is indeed what's happening because integers are simple values with known fixed size, and these two 5 values are pushed onto the stack. Now we'll look at string. Request memory from the operating system for a string called S1 and give it the value of hello. This is on the heap at this point. This looks very similar to the previous. Oh, and then on S2, set it equal to S1. But that's going to share memory, I would assume. So we might assume that the way it works would be the same. That is, the second line would make a copy of the value S1 and bind it to S2, but that isn't quite what happens. So, and figure 4.1 to see what's happening to the string under the covers. A string is made up of 3 parts shown on the left: a pointer to the memory that holds the contents of the string, a length, and a capacity. This group of data is stored on the stack. On the right is the memory on the heap that holds the content. Right. Okay, so this pointer is going to be a memory address pointing over to the heap. On the heap, you're going to have the size of the memory. our capacity is 5, our length is 5, so this is all the memory on the heap. So this bit would start it, this bit would end it, or I should say byte, because it's going to be a car. So it's a 1, 2, 3, 4, 5 byte section of memory on the heap that's been allocated. The length is how much memory in bytes. Yay! So I'm verifying things. The contents of the string is currently using. The capacity is the total amount of memory in bytes that the string has received from the operating system. The difference between the length and the capacity matters, but not in this context, so for now, it's fine to ignore the capacity. It's going to matter when you exceed the capacity. You're going to have to create a new place on the heap, up the amount of memory in bytes you can store, update the pointer to point to the new memory address, and then clean up the old memory's address, that 5 bytes that were allocated, clean that up and tell the system that, hey, these are available for allocation again. Okay, so the difference between, when we assign S1 to S2, the string data is copied, meaning we copy the pointer, the length, and the capacity that are on the stack. We do not copy the data on the heap that the pointer refers to. In other words, the data represented in the memory looks like this. Yeah, so sure, we have 2 different variables on the stack, but they both point to the same place, they both have the same length, and they both have the same capacity. Which means if S2 exceeds the capacity, and we have to free up the memory and reallocate new memory for a bigger string, that's going to have to backpropagate to all the pointers that are associated with this referenced memory address. It doesn't make a copy, right? So it's not as though, so when you change hello to hi, it'll change S2 to hi as well. Unless you do a deep copy, which I'm not sure what that looks like in Rust yet. Earlier we said that when a variable goes out of scope, Rust automatically calls drop function and cleans up the heap memory for that variable. But in 4.2, the figure shows both data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. This is known as a double free error and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety, there's one more detail to what happens in this situation in Rust. Instead of copying the allocation or allocated memory, instead of trying to copy the allocated memory, Rust considers S1 to no longer be valid, and therefore Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. Oh. Use of moved value. Rust prevents you from using the invalid reference. So it's got like reference invalidation. If you've heard the term shallow copy and deep copy while working with other languages, the concept of copying the pointer, length, and capacity without copying the data probably sounds like making a shallow copy. But because Rust also invalidates the first variable, instead of being called a shallow copy, it's known as a move. In this example, we start saying that S1 was moved to S2. What actually happens is shown in 4.4. Invalid, still pointing, still pointing. When we clean this up, we're going to remove it from the heap and then delete both of these stack records, and we're going to inform the OS that we have free memory for it to handle. With only S2 valid, when it goes out of scope, it alone will free the memory and we're done. In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. Any automatic copying. Very cool. Ways variable and data interact. Clone. Oh. Ways data and memory interact. Where did it go? Oh. Okay. Clone. If we do not want to deeply copy the heap data of the string, if we do want to deeply copy the heap data of the string, not just the stack data, we can use a common method called clone, which I think I messed with in the last video. We'll talk more about it in chapter 5, but because methods are a common feature in many programming languages, you've probably seen them before. So you just say S2 is equal to S1 clone, and then you're going to end up with this, right? So you're going to have two of the same length in bytes allocated in the heap with the same values for each byte. Yeah. And then when you clean up S1, S1 would go away here. So that would go away, but S2 would still be valid, and then it would clean up its own memory. When you see a call to clone, you know that some arbitrary code is being executed and that code may be expensive. It's a visual indicator that something different is going on. Stack-only data copy. There's another wrinkle we haven't talked about. This code using integers, part of which is shown in 4.2, works and is valid. Yeah. Right. But this code seems to contradict what we just learned. We don't have to call clone, but X is still valid and wasn't moved into Y. It's because they're on the stack already, right? The same reason that types such as integers have a known size, had compile time, and are stored entirely on the stack, so copies of the actual values are quick to make. That means there's no reason we would want to prevent X from being valid after we create the variable Y. In other words, there's no difference between deep and shallow copying here, so calling clone wouldn't do anything different from the usual shallow copy, and we can leave it out. Or we could put it in. Rest has special annotation called the copy trait that we can place on types like integers that are stored on the stack. We'll talk more about traits in chapter 10. If a type has the copy trait, an older variable is still usable after assignment. Rust won't let us annotate a type with the copy trait if the type or any of its parts has implemented the drop trait. So copy will only work on the stack, and anything on the heap needs the drop state. If the type needs something special to happen when the value goes out of scope and we add the copy annotation to the type, we'll get a compile time error. To learn about how to add copy, see derivable traits in Appendix C. We'll look at that later. So what types are copy? You can check the documentation, which I will do. But as a general rule, any group of simple scalar values can be copy, and nothing that requires allocation or is some form of resource is copy. So integers, booleans, floats, chars, tuples because they're fixed size, and I would imagine arrays if they only contain types that are also copied, then that's why array is not. Which is interesting. I think because arrays are fixed size, one type, so I figured the same rule would apply as if that type were a copy, then it would fit in this category. I'm going to assume that that's the behavior, and we can test that later. All right. The semantics for passing a value to a function are similar to those for assigning a value to a variable. Passing, hey, welcome back. Good to see you. Good evening yourself. we're going through ownership of Rust right now, and I'm just sort of solidifying in my head what goes on the stack with the copy trait and what goes on the heap with the drop trait. Passing a variable to a function will move or copy. Passing a variable to a function will move or copy just as assignment does. Okay. Listing 4.3 has an example with some annotations showing where variables go into and out of scope. So, into scope here takes ownership s. S's value moves into the function, so it's no longer valid here. Interesting. Let's take that. They said they weren't going to show main, and they certainly still are. Okay, so we're going to touch scope ownership, .rs, and then in here we'll just say scope ownership, and then cargo run, and then vim scope ownership. Okay. Hello 5. So if we were to print line s, what happens? Boom. Oh, keep doing that. I keep doing it. I'll keep doing it forever. Pass in the token. Okay, now we get the error. Value, yeah, borrow of moved value s, value borrowed here after move. So what happens is we've passed ownership into ownership, and we can print it. Now, if this function were to return, I'm sorry, it's this one, return a string, and we just said return some string, and then back here we said s2 is equal to, and we'll say let, and then we print s2, what happens? Perfect. So we pass in the string scope, we then take the ownership of that. Let's zoom in on this. Take our ownership. Here we print out some string, which is a moved pointer. So we've got two pointers, one pointing to, or they're both pointing to the heap. And then we return some string. Well, the moment we return some string, we exit the scope. Some string is now freed up. So both those pointers are now deleted. Only one calls drop. The heap gets dropped, and a new allocation then is allowed to take place on S2. So a new pointer is created, and that pointer points to a new heap. So even though we're not changing the value at all, we have to do this heap management and this allocation and freeing of memory on the heap just to pass one variable, one string, to a function and return that same string out. So that's a consideration that has to be taken, and that's just, as far as I understand, inherent of Rust. Okay, so that makes sense. Return values and scope. Returning values can also transfer ownership. Oh, really? Okay, so exactly what I just talked about. Return some string transfers ownership. So it doesn't drop it. Okay, let's figure out the behavior here. Okay, ownership S2 comes into scope. So let's go to give. S1 gives ownership. Gives ownership. let some string, because we let in here, comes into scope, some string is returned, moves out of the calling function, but isn't cleared up because it was returned. S2 comes into scope. S2 is moved into takes and gives back. Okay, that's what we want to look at. Which also moves its return value into S3. So takes and gives back, takes a string, returns a string is returned, and moves out the calling function. So technically what I did here, because we didn't mutate this string at all, we are just moving. So really what we end up with is 3 pointers and 2 disabled pointers. S1 and some string are the disabled pointers. Then we have S2 as a pointer that points over to the same heap of memory. So really we're just stacking, we're putting variables on the stack pointing to the same heap. Cool. That makes me feel better. Ownership variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes data on the heap goes out of scope, the value will be cleaned up. That uses data on the heap will be cleaned up by drop unless the data has been moved to be the owner by another variable. Okay. Taking ownership and then returning ownership with every function is a bit tedious. What if we want to let a function use a value but not take ownership? Stuff that leads to heap allocation is usually very explicit. You'll see new or clone, yep, or from, right? So from here becomes very explicitly heap allocation. Okay, so what if we want a function to use value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we want to use it again. In addition to any data resulting from the body of the function, I feel like an annotation is coming here. In addition to any data resulting from the body of the function that might want to return as well. It's possible to return multiple values using tuple. Okay, so allocate memory, assign it to S1, creates a pointer in a heap. S2 and length are going to be calculate length, and then we pass in S1. That comes in as S as string, and we're going to return string and a use size, which is going to be like on a 64-bit system, unsigned 64. Let length equal to s.len and return s in length. I didn't realize you could have multiple returns through a function. That's great. So that's like Go. But this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for this concept called references. So we're going to pass the ampersand in, and then we're going to dereference. So asterisk on the other side. Let's find out. References and borrowing. All right, so ampersand in, and ampersand on this side. So in our example, so we can copy scope ownership, and we're going to name it scope references. And then we'll just references. Okay, and then we'll cargo, I guess we should do it down here, cargo run. Okay, and vim scope references. So now we can just say delete t, ooh. Okay, do it again. Okay, so take ownership, but it doesn't, it does something else, but we're not gonna worry about renaming it. Let's do that, and then we'll print s. It's gonna be angry. which one does it go on to? Onto the type. Type of a reference of a string, and it returns nothing. Okay. There we go. And now we can just run that and everything is fine, right? So that's just a reference that does not transfer ownership, but because it doesn't transfer ownership, if I were to try to return the reference, we get an error saying expected string found reference. Yep. Cool. Makes total sense. S is a pointer to a pointer, or sorry, it's a stack with a pointer to a stack that has a pointer to a heap. The opposite of referencing by ampersand is dereferencing, which is accomplished with the dereference operator. We'll see some uses. So could we like return a dereference of some string? Move out of borrowed content. Cannot move out of borrowed content. Okay, I'll have to, I don't know what that means yet. Okay, let's take a closer look at the function call here. Reference S1 syntax lets us create a reference that refers to the value of S1 but does not own it. Because it does not own it, the value it points to will not be dropped when the reference goes out of scope. Just the reference itself, I would think, would get popped off the stack. Likewise, signature of a function uses ampersand to indicate the type of the parameter S is a reference. Let's add some explanatory annotations. Okay, the scope in which the variable S is valid is the same as any function parameter scope, but won't drop what the reference points to when it goes out of scope because we don't have ownership of it directly. Because a pointer doesn't point to the heap, it points to another item on the stack. We won't need to return the values in order to give back ownership because we never had ownership in the first place. We call having references as function parameters borrowing. As in real life, if a person owes something, you can borrow it from them. When you're done, you have to give it back. So what happens if we try to modify something that we're borrowing? We're going to get an error that says cannot borrow immutable borrowed content. Okay. Just as variables are immutable by default, so are references. We're not allowed to modify something we have a reference to by default, but we can fix the error in the code with a small tweak, making the reference mutable and passing in a mutable version of S, mutable reference, and then we have a mutable reference to a string. And first we had to change S to mutable, then we had to create a mutable reference. Yeah. Exactly what I said. They have one big question. You can have only one mutable reference to a particular piece of data in a particular scope. This would fail. We have two references that both reference S. It would say cannot borrow S as mutable more than once at a time. And this allows us to have memory safe mutability of a single chunk of data on the heap. It's something that new Rustaceans struggle with because most languages let you mutate whenever you'd like. The benefit of having this restriction is Rust can prevent data races at compile time. Right. Data race is similar to a race condition and happens when these three behaviors occur. Two or more pointers access the same data at the same time. At least one pointer is being used to write to the data. There's no mechanism being used to synchronize access to the data, right? Like a mutex. Data races cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down at runtime. Rust prevents this problem from happening because it won't even compile code with data races. As always, we can use curly braces to create new scope, allowing for multiple mutable references, just not simultaneous ones. Okay. Oh, you can just create scope wherever you want. Interesting. So in that scope, you can then run functions. Okay, understandable. A similar rule exists for combining mutable and immutable references. So you've got a mutable string, and then you've got a reference to that string and another reference to that string, and then you create a mutable reference to that mutable string. Big problem. Cannot borrow s as mutable because it's also borrowed as immutable. Okay. We also cannot have a mutable reference while we have immutable ones. What just happened? You have to let go. Stop posting links. Oh, no, hang on. Let me look into Nightbot. It's not properly configured yet. Hang on. I'll look at the logs too to see the link. Kind of related. I'll check that out. And then let me go to our, what would it be? Spam protection. Links, disable. Excess emotes, disable. Excess caps, I'm going to disable. We'll leave the blacklisted words and phrases. That's all we care about here. Okay, you should be able to post those links now. It shows the generated assembly for many programming or many languages / compilers. Okay. I don't know what that means. Hang on. So we specify Rust as a language. What does this Vim thing do? Do I really have Vim control? Oh, yes. Thank you. Okay. So let's make this full screen for the moment. Okay, so this really did, just go straight into the machine code. Oh, cool. Okay, this gets bookmarked for sure. How do we do that? Here we go. Compiler Explorer. Cool. Thank you for that link. Just made a simple function that goes through a range of numbers and sums it up. Great. Yep. Awesome. I'll definitely check this out in more detail. And when I know more about it, I might even do a stream on it. Who knows? All right, so I'm going to pin this, actually. I really like that. Okay. Whew. We also cannot have a mutable reference while we have an immutable one. Users of immutable references don't expect the values to suddenly change out from under them. However, multiple immutable references are okay because no one can change the data. Note that references scope starts from when it is introduced and continues through the last time the reference is used. For instance, this code will compile because its last usage of the immutable reference occurs before the mutable reference is introduced. So we have immutable references, and then we print them out, and then we create a mutable one, and at that point, I imagine that these two are decommissioned off the stack, and this one is put on the stack and points at the mutable heap, because the heap string is mutable. Okay. The scope of the immutable references R1 and R2. Yep, I understand. I just said that. Dingling references. In languages with pointers, it's easy to erroneously create a dingling pointer, a pointer that references a location in memory that may have been given to somebody else, by freeing some memory while preserving a pointer to that memory. By freeing some memory while preserving the pointer. In Rust, by contrast, the compiler guarantees that references will never be dangling references. Correct. If you have a reference to some data, the compiler will ensure the data will not go out of scope before the reference to the data does. Makes sense. Let's try to create a dangling reference with Rust. It will prevent it at compile time, and it will say expected lifetime. This is the lifetime people are talking about. Got it. Missing lifetime specifier. So we reference to nothing dangle. Dangle will return a reference to a string. Let string from this return the reference, and it says this function's return type contains a borrowed value, but there is no value for it to be borrowed from. The error message refers to a feature we haven't covered yet, lifetimes. We won't touch lifetimes until chapter 10, but if you disregard the parts about lifetimes, the message does contain certain key to why this code is a problem. Yeah, but there's no value, right? Let's take a closer look at exactly what's happening at each stage of our dangled code. Dangle returns a reference to a string. S is the new string. We return a reference to string. Here it goes out of scope and is dropped. Its memory goes away. Right. So, yeah, makes sense. Because S is created inside dangle, when the code is finished, S will be deallocated. When we try to return a reference of it, that means this reference would be pointing to an invalid string because the heap would have been cleaned up. Rust won't let us do that at compile time. And the solution is not to return a reference, but just to return the string. And then ownership gets transferred to whoever called no dangle, which means we have a new pointer to the same heap. Rules of reference is at any given time you can have either one mutable reference or any number of immutable references. References must always be valid. Okay, next we'll look at a different kind of reference, slices. So let's see where we are in our ownership, the slice type. So this will be the last thing I can do before I jet out of here. So let's go ahead and go through this. Just a moment. Okay. Another data type that does not have ownership is the slice, because, well, then that means it's going to be a fixed length and it's going to go on the stack. Slices let you reference a contiguous sequence of elements in a collection rather than a whole collection. If I have time, my background, or what other languages do I really use? Yeah, I've got time. So my background is I'm self-taught. I've been programming professionally for 10-ish years. Started out with HTML, CSS, JavaScript. Then I learned PHP. Then I learned Python. Then I really learned JavaScript, which is different than what I was doing initially, which was jQuery. And then just through the years, I've sort of picked up other languages and learned them. Go is a go-to favorite language of mine, and now I'm learning Rust because I want to be able to. I just want to work with more efficient and more type-safe languages, and they're fun for me to learn. There's less crazy behavior like you see in JavaScript, and with WebAssembly, Rust looks like it would be a really good candidate for that, as does Go. So yeah, that's sort of the elevator pitch of my progression through languages. Yeah, similar to yours. Yeah, I find a lot of people, especially when they're self-taught, that's like the trajectory, that's the path that's followed. If you go through comp sci in college, you're going to be doing a lot of Java, maybe Python. So I haven't been through Go, but had Java, yep. I really like Go. Go is really nice to type. Like, the syntax all makes sense. The behaviors make sense for the most part. There are it's declarative enough and expressive enough, but it's also simple. Like, you don't have classes or extension. Instead, you have packages and importing. So it's like simple by design. They don't have generics. They're working on that for Go 2. Was just at GopherCon where they talked about that. But at this point, I'm not even sure if Rust has generics, right? So I'm just going to slowly uncover this stuff through the book, which is not typically how I learn languages. So this will be an interesting deep dive into a language. Okay, so here's a small programming problem. Write a function that takes a string and returns the first word it finds in that string. So search till white space. If the function doesn't find a space in the string, the whole string must be one word, so the entire string should be returned, or it's empty. Let's think about the signature of this function. Well, it should return... Well, what is it doing? Takes a string and returns the first word. So it's going to return a string because it's going to essentially copy that string out of the string that's passed in, I would think. Okay, so this function, first word, has a reference string as a parameter. We don't want ownership, so this is fine. But what should we return? We don't really have a way to take or talk about part of a string. Oh, okay. I should have realized they were going to talk about slices. However, we could return the index of the end of the word. So let's try that. Okay. The first word function that returns a byte index value into the string parameter. Okay? Because we need to go through the string element by element and check whether the value is a space, we'll convert our string into an array of bytes using as bytes. And that's a method on the strings module. I'm not sure what they're called in Rust yet. Crate? I don't know. Next, we create an iterator over the array of bytes using the iterate method. Iterate, enumerate. So we're going to get index and value. We'll discuss iterators in chapter 13. For now, iterator is a method that returns each element in the collection, and the enumerate wraps the results of iterator and returns each element as part of a tuple instead. Okay. The first element of the tuple returned from enumerate is the index, right? And the second is a reference to the element. Okay? This is a bit more convenient than calculating the index ourselves. I'll agree with that. Because enumerate methods return a tuple, we can use patterns to destructure that tuple, just like everywhere else in Rust. So in the for loop, we specify a pattern that has I for the index and tuple and item reference for the single byte in the tuple. Okay, because we get a reference to the element from enumerate, we use ampersand in the pattern. Inside the for loop, we search for the byte that represents the space by using the byte literal syntax. Okay, byte being B and then single quotes on either side. If we find a space, we return the position. Otherwise, we return the length of the string by using s.len, right? Okay. We now have a way to find out the index at the end of the first word in the string, but there's a problem. We're returning a unsigned integer, say U64, on its own. But it's only a meaningful number in the context of the string reference. In other words, because it's separate from the value from string, there's no guarantee that it will still be valid in the future. Consider for 8 that uses first word. So we create a word, a mutable string called s, and then we pass the reference to first word, and then we get word back, and then we clear s. Word is going to be 5. This empties the string on whatever line that is, s.clear, to be empty. We still have the value of 5, but there's no more string, right? So what do we do? This program compiles without any errors and would also do so if we used word after calling s.clear, because word isn't connected to the state of s at all. Word contains the value 5. Understood. This is very contrived. Having to worry about the index of word getting out of sync with the data is tedious and error-prone. Agreed. Managing these indices is even more brittle. Agreed. With the second word, yeah. Okay. So we're tracking and starting. Right. So this would be like the start of the index, and this would be the index. Okay, so enough of that nonsense. It's painful to even look at. So now what we're going to do is a string slice is a reference to a part of a string, and it looks like this. Okay, perfect. This is similar to taking a reference to the whole string, but with the extra 0 through 5 bit. Rather than, they call it a bit? Wouldn't that be? Yeah. Anyway, rather than a reference to the entire string, it's a reference to a portion of the string. We can create slices using a range with brackets by specifying the starting index and the ending index. Right, bit as in bit of code or text. Yeah, part. They should, yeah. I'd rather they not mix words around when talking about languages that operate on bits and bytes and, Anyway, semantics. Cool. So we create slices with the starting index to the ending index, where the starting index is the first position in the slice and the ending index is one or more than the last position in the slice. Internally, the slice data structure stores the starting position and the length. Okay, the data structure for the slice. Oh, they're going to show it to us. Perfect. Stores the starting position of the length of the slice. Oh, and the length of the slice. Got it. Which corresponds to the ending index minus the starting index. So, for reference S, 6 through 11, world would be a slice that contains pointer, very good, to the specific byte. Okay, so it's just like, hey, we have this information on a heap. We're going to go ahead and create world, and it's going to start at 6 and go to 11. What about what about if we didn't go to 11? Right? What if we went to 9? Oh, then it would be a pointer to 6, length 4, and that would be 1, 2, 3, 4, whirl. Got it. Upper bound is always exclusive. Right, yeah, for sure. With Rust's ... range syntax, if you want to start at the first index 0, you can drop the value before the 2 periods. Okay, perfect. So, assumed 0. And then this goes to the end or to the length. Are these the same thing? You can drop the trailing number. This means these are equal. Yeah. Got it. You can also drop both values to take a slice of the entire string. So these are equal. I'd like to know why you would want to do that, but maybe you do. String slice range indices must occur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. If you attempt to create a string slice in the middle of a multi-byte character, like UTF-16, for the purpose of introducing string slices, we're assuming ASCII-only characters. In this section, a more thorough discussion of UTF-8 handling is in Chapter 8. You do it because it's a different data type. Okay. Yeah, I'll have to understand that more as we progress. With all this information in mind, let's rewrite first word to return a slice. Okay. Slice. Okay. The type that signifies string slice is written at reference of str. Okay. I'll just have to know, assume lower cases, abbreviated, are going to be slices of types. But I don't know. That's just an assumption. So we get a string in. We convert it to bytes, right? So we have now, this is not a reference change. This is a new pointer or a new object on the stack with a pointer over to a heap allocated chunk of memory. And then we get the index and the reference to the item by iterating and enumerating into a tuple. If item is equal to a byte space, an ASCII space, I think, or it's more than those, but I'm not sure. So an ASCII space, then we are going to return from 0 to I, and we know it's going to be 0, so we could drop 0 off, .i, because we're looking for the first word, so we don't need to track the other index. It can always be 0. There's caveats to that, because maybe the sentence started with a space for some reason. But anyway, and then we return the full slice, the full reference to the word if nothing is found. But we need to return a slice. That's why, okay, that makes sense, right? So we have to return a slice of string. So we do the whole thing when we don't find a word. Got it. Okay, so we get the index for, yep, I already went through all that. Returning a slice would also work from the second word. We have a straightforward API that's harder to mess up because the compiler will ensure references into the string remain valid. So the bug in listing 4.8, when we got the index and the end of the first word, but then it was cleared, that code was logically incorrect. Okay, so basically what it's saying is we get the word as a reference, or as a string slice, we clear it, and we get an error, and the error says cannot borrow s as mutable because it's borrowed as immutable. Yeah. Okay. Borrowing rules that if we have an immutable reference to something, we cannot also take a mutable reference. Because clear needs to truncate string, it needs to get a mutable reference. Right. Rust disallows this, and compilation fails. Not only has Rust made our API easier to use, but it has eliminated an entire class of errors at compile time, which is key. Okay, so that makes sense. Recall that we talked about string literals being stored inside the binary. Now we know about slices. Makes sense. Slice as parameter, right? So you can pass that in. Makes sense, and you can return one. Makes sense. Could be a subslice. Okay. If we have a string slice, we can pass that directly. If we have a string, we can pass that. Pass a slice of the entire string, defining a function to take a string slice instead of a reference to a string makes the API more general and useful without losing functionality. So we get my string from memory, call it hello world. It's now in the stack for my string, heap for the value. We get a word for first word. We pass in first words work on slices of strings, so we pass in the whole slice, and we get a slice back. And then from my string literal, first words also, or word works on slices of string literals. Right, so we can just slice a slice again. Because string literals are string slices already, this works too. Right. Perfect. Makes sense. Other slices, string slices, as you might imagine, are specific to strings, but there are more general slices too. Consider an array. Okay, so an array is a slice. Or no, an array can be sliced. Got it. Just as we might want to reference part of the string, we might want to refer to part of an array, and we would use the same syntax to do so. This slice has the type of a reference, of an array, of an integer 32-bit. Works the same way as string slices do by storing a reference to the first element and the length. You'll use this kind of slice for all sorts of other collections. We'll discuss these collections in details when we talk in Chapter 8. So, ownership, borrowing, and slices ensure memory safety in Rust. Rust language gives you control over your memory usage in the same way as other systems programming languages, but having the owner of the data automatically clean up the data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Ownership affects how lots of other parts of Rust work, so we'll talk about these concepts further throughout the rest of the book. For now, we're going to stop streaming at this point. So this was the first, cursory look into ownership and the behaviors of it and how stacks operate and how the heap is allocated and how Rust handles drop behind the scenes after the end of a curly brace of a function to drop the stack and clean up the heap. We can pass ownership around by passing in a variable into a function. If we don't want to shift ownership, we can just pass it by reference with an ampersand. We went into slices and how we can create a stack reference, basically, that points to a byte of a already existing heap allocation, and then gives a length and can read the whole thing. And that's just how slices work. That's nothing too crazy. And then in Chapter 5, we're going to be looking into grouping pieces of data together in a struct. And structs are common through other languages, including Go. So I'm curious to see how it differs in Go. So I'll probably be streaming that in the next couple of days. I'm going to, right now, head out, grab some dinner, get this uploaded to YouTube, and I will see you next time. Yep, thanks for coming, EverX. And I will enjoy the meal. Talk to you later.